So this is hopefully going to be our last lecture dealing with the condition of angular momentum and its different manifestations. So in the previous lecture we looked at the fine structure. The fine structure was treated as a perturbation to the Coulombic energies. And we found out that up to first order, the energy shifts are given by minus mc squared alpha fold 2nq 1 over j plus half minus 3 over 4n. So these were the energy shifts. And we also noticed that the the degeneracy in the n subspace is lifted. And the new relevant quantum numbers are the nj numbers. And if you look at the total Hamiltonian now, which is now a combination of the Coulombic Hamiltonian plus the kinetic energy as well as the spin orbit interaction plus the relativity interaction, then the quantum states which are ideal states of this Hamiltonian are the states that are represented by n, l, s, j. Okay, so these coupled states are the ideal states of this Hamiltonian. Okay. And the commuting set of compatible set of commuting observables is L squared, S squared, J squared, and of course the J squared comes Jz. So this is from the previous lecture on the fine structure interaction, and we also noticed that we could define quantum states with the same energy by the term symbols. For example, we can have S half, 1s half, we can have 2s half, we can have 2p half, 2p 3 by 2. So these energy levels, for example, will have different energies because they have different values of J. So this was the fine structure interaction, where these terms are treated as perturbations, and then we apply degenerate perturbation theory to find out how these Coulombic energies will change. Okay. My first question is that if, for example, we have a state 2p 3 by 2, this is a particular energy level. Previously, all of these three levels were degenerate because they had the same value of n, and the energy to zeroth order, which means the unperturbed energy, was simply given by minus mc squared alpha squared over 2n squared. It only depended upon n. But now states with the same m but different values of j, they come non-degenerate, they have different energies. So the spin orbit interaction has lifted the degeneracy. It has unveiled the finer structure within the n subspace. That's what the spin orbit interaction has done. Now what we would like to find out is what happens when we have spin orbit interaction, the relativistic correction, and on top of it we place the attendant side of the magnetic field. So what we're going to look at now is the Zeeman effect, as it is called. And we're going to look at the aspect of Zeeman effect which is called the anomalous Zeeman effect. Now my first question is that this quantum state, NLSJ, which is defined by these labels, it's a coupled state. It's an eigenstate of H0, of HR, as well as HS0. What's the degeneracy of this state? Is it a D? Is there an even internal structure within this state? For example, how many levels would correspond to how many electrons, for example, can come into this state?
For 1 per second.
For one NLSJ, for this quantum How many electrons can get into this? How many electrons is it possible to have? How many electrons with all with the same quantum state? Only one?
Two or four.
No, the degeneracy has already been lifted because that's why we have defined a J. So how many values of Mj are possible?
So there are four electrons can come into one state. Because there are two Mj values.
How many Mj values does this state have?
Two.
Why two? What's the value of J? You don't know. There are two J plus 1 values of Mj that are embedded within the state. And the electron can have two spins. It can have two values of Ms. So there are 2 times, this is a 2 times 2J plus 1 degenerate state. Now how do we lift this degeneracy? We apply magnetic field. We know that if I have, it's common knowledge, that if I have, say, a single isolated electron with a spin s half, okay, there will be 2 energy levels within this. One will be half, the other will be half minus half, corresponding to the 2 values of Ms. And when we place this inside a magnetic field, which means that we apply a Hamiltonian, let's call it the Zeeman Hamiltonian, which is, say, some G E over 2m SZ. Okay, so we apply a magnetic field along the Z direction. So this is the Hamiltonian that is applied, where G is the Lambda G factor. For spin half electron, its value is 2. So we apply this, or you can also write this as some omega naught SZ, doesn't matter. This is just a frequency. Or you can also write this as G mu B over H bar SZ, where mu B is the Bohr magneton. So all of these possible variants of the just represent the same Hamiltonian. So if you apply a magnetic field, which means you're subjecting the spin half particle to this Zeeman Hamiltonian, this means that this degeneracy will be lifted. Okay, we've seen multiple examples of this kind, both in our Quantum Mechanics 1 course and the Quantum Mechanics 2 course. This degeneracy is lifted, and these states will now acquire different energies. One will be lower in energy, the other will be higher in energy. And this energy, for example, if this value is 2, this energy is going to be 2 mu B over 2, which is 1/2. This is the eigenvalue of Sg, which is mu B. And this energy is going to be minus mu B. And this energy splitting is going to be 2 mu B. B, with a B as well. So this is how the energy is split up. One level requires a higher energy and the other level requires a smaller energy. So how do you find the energies? You just find the eigenvalues of Sc, which are Ms H bar, plus minus half. Okay, and the half cancels out with G. So this is the basic concept of the Zeeman effect. Now what we have is we have an NLSJ state. NLSJ state, right? It's 2 times 2J plus 1 fold degenerate. So what we expect is that corresponding to the different values of Mj, which range from J minus 1, J minus 2, all the way up to minus J. These are 2J plus 1 levels of Mj. The degeneracy will be limited. Now let's look at this from the perspective of perturbation theory. From the perspective of perturbation theory, what we have now, we would like to find out the energy of these two states. Right? That's the goal. The degeneracy has been lifted to certain energies. What are the corrections to the unperturbed energies, in other words? Is the course getting more and more complicated? Sorry. ये नहीं समझ आ रहा।
कंफ्यूजन हो जाती है।
जितना काम करोगी, उतने होमवर्क प्रॉब्लम्स करोगी, जितने एक्सरसाइजेस, चैप्टर 12 के बैक चैप्टर प्रॉब्लम्स नहीं करो, ठीक है, उससे बहुत अच्छी आपको समझ आएगी। अच्छा, अब आप ये देखिए कि the Hamiltonian is now the background Hamiltonian, the relativistic correction, spin orbit correction, plus the Zeeman interaction. Okay. Now, if this is a weak magnetic field, which means that this interaction is much smaller than these other interactions, then we can treat this as the unperturbed Hamiltonian and we can treat this as the perturbed Hamiltonian. And what do I mean by weak? Weak means, now the spin orbit interaction comes out because the electron effectively sees a magnetic field because of the presence of the proton. So there is an internal magnetic field. Say that magnetic field is of the order of 60 Teslas. If you work it out, the rough number you would get is 60 Teslas for the hydrogen atom in its ground state. So magnetic fields that are weaker than this can be treated as weak magnetic fields. And then this Zeeman Hamiltonian can be treated as a perturbation. So now let's look at what the Zeeman Hamiltonian is. Okay. The unperturbed quantum states, remember, are N, L, S and J. Right? These are the unperturbed states, which are the coupled states. These are the good quantum numbers, in other words. Okay. So in the unperturbed Hamiltonian, remember that the individual Z components of the orbital and spin states, they are not good quantum numbers. Now what we would like to see is that the Zeeman, we would like, first of all like to write out what the Zeeman Hamiltonian is. The Zeeman Hamiltonian is going to be mu b over h bar g times s sg plus g times l lz. Okay. So sg is the spin angular momentum, lz is the orbital angular momentum, and in one of its projections, the field is applied along the z-axis. Now, GL is 1, the orbital angle, the Lagrange factor, and this is 2. This comes out from a classical calculation. You can find out the current due to a circulating electron around a proton, and you can find out its magnetic moment using Ampere's law. This turns out to be 1. This is 2. This comes out because of relativistic quantum mechanics, the Dirac equation. So really our Hamiltonian is mu b over h bar 2 times sg plus lz. Now this is our perturbative Hamiltonian and these are our unperturbed states. Now we would like to find out how the energies change because of the presence of this Hamiltonian. The unperturbed energies are over there, right at the top. Okay, so now these become the unperturbed energies. So I can write the unperturbed energies E, N, J. Now these are to 0th order, means the unperturbed energies. Because now I'm treating the Zeeman Hamiltonian as a perturbation. So these are minus mc squared alpha 4 divided by 2 n cube 1 over j plus half minus 3 over 4i. ठीक है? अब हमने क्या करना है? We would like to apply perturbation. The first question is whether we apply degenerate or non-degenerate perturbation. Why do?
Because we have 2 into j plus 1 plus 2.
Right. Because we have some degeneracy that exists. So how do we solve degenerate perturbation? We write this Hamiltonian in the subspace, in a degenerate subspace. Okay. So for a given n and j, right? For a given value of n and a given value of j, there is a subspace that is formed. which is of a certain dimensionality. That subspace is 2j plus 1/4 dimension if we ignore the spin. Okay? So we have to write this Hamiltonian in that subspace. Now this Zeeman Hamiltonian Hg comprises Sz and Lz terms. G. This Hamiltonian comprises Sz and Lz terms. But these coupled states, which are eigenstates of the unperturbed Hamiltonian, are not eigenstates of Sz or Lz. So what we really would like to have are, if you would like to write a matrix, let's suppose, now this matrix will be infinite dimensional because there are infinite possibilities of n and g. Let's suppose we just take one chunk of the matrix. Suppose n is 2. If n is 2, n can be 0 or 1. Okay, if L is 0, then J can be half. The only possibility is half. If L is 1, J can be 1/2 or it can be 3/2. Okay, so the states, the basis states for this degenerate subspace are, for n equals 2, right? The n equals 2. And let's suppose n equals 2 and j equals half. Okay. And for n equals 2 and j equals half. This will comprise a basis, right? This will comprise a subspace. Okay, all of these, the basis states of this subspace are, now I'm dropping out the n equals 2, are j equals half, nj equals half. Okay, so this is j, this is nj, and I have j equals half, nj equals minus half. So this subspace is spanned by two basis vectors. Likewise, if I take n equals 2 and j equals 3/2, if I take n equals 2 and if I take j equals 3/2, then my subspace will have more vectors. It will have j equals 3/2, nj equals 3/2, j equals 3/2, nj equals half, j equals 3/2 and j equals minus half, j equals 3/2 and j equals minus half. So this is a 4-fold degenerate subspace because 2 times 3/2 plus 1 is 4. I'm ignoring the spin. This is a 2-fold degenerate subspace. So these basis vectors form one subspace, degenerate subspace, because both of these vectors have the same value of n and j. So both of these, if the electron lies in either of these states, it will have the same energy. If we are not yet considered the Zeeman interaction. Likewise, these states will have the same energy because they have the same value of n and the same value of j. Now what we would like to do is we would like to write the Zeeman Hamiltonian Hd in the degenerate subspace. So we have to choose a basis for the degenerate subspace. Now that basis could be these states. So if you are focusing on n equals 2, if you are focusing on n equals 2 only, then the subspace comprising n equals 2 will comprise of 6 vectors, and Hg will be a 6x6 matrix. Okay.
जी हैमिल्टोनियन में एक बीम आना चाहिए टू डिस्क्राइब द स्ट्रेंथ ऑफ द मैग्नेटिक फील्ड.
ठीक
B
है,
mu
B mu B
is a constant.
इस तरह ये यहाँ पे ये ओमेगा नॉट ठीक है। तो 6x6 मैट्रिक्स होगा ना इन दी n equals to subspace. This subspace comprises two degenerate subspace. One is made up of these two vectors, one is made up of these four vectors. So it will be 6x6 matrix. Okay. Now we have to choose. We would like to write this matrix in a particular basis. So the basis we can choose. There are different choices of basis. One is this possible basis. Okay. Then we diagonalize that matrix. The eigenvalue of that matrix will give us the energy conditions. Okay. So this is. I would like you to write out this matrix explicitly as part of your homework. It's one of the questions at the back of the chapter. Now let me show you what this matrix looks like. And how would you write this matrix? So I'm solving this weak magnetic field problem using a long route, but you have to do this mechanically once. Okay. So HZ will be a 6x6 matrix. Okay. And now I have to do the ordering of the basis states so that I am able to write this matrix or represent this matrix on a particular basis. Okay. So the ordering that I can choose is so 3 by 2, 3 by 2, 3 by 2, half, 3 by 2, minus half, 3 by 2, minus 3 by 2, half, 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 minus half. Okay? So this is the n equals to subspace, and the first four rows correspond to j equals 3 by 2, and the bottom two rows correspond to j equals half. And how do I label the columns? I label them in the same order: 3 by 2, 3 by 2, 3 by 2, half, 3 by 2, minus half, 3 by 2, minus 3 by 2, half, 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 minus half. Okay. Now the second thing is that I would have, now this is a 6x6 matrix, 36 elements in this matrix. So this is HZ. I can do this HZ, however, is proportional to 2 times SZ plus LZ. Okay? So I will have to find out LZ separately, I will have to find out SZ separately. And then I will have to do LZ plus 2 times SZ. And I will get HZ. Okay? देखो HZ कैसे फाइंड करेंगे? HZ फाइंड करने के लिए आपको SZ भी कभी LZ का फिर दोनों को ऐड करेंगे. ठीक, और रिमेंबर दिस इज फर्स्ट ऑफ ऑल LZ. माय फर्स्ट क्वेश्चन इज will LZ in itself be diagonal in this basis? The basis we chose. No, because LZ has different eigenstates from these states. These are coupled basis states, coupled states. Whereas LZ is uncoupled states as its basis, as its eigenbasis. Similarly, SZ will not be diagonal. So HZ in general may not be diagonal. Okay. LZ plus SZ, which is JZ, may be diagonal. And in fact, it is diagonal.
So there are 2 SZ plus LZ.
तो मैं वैसे कह रहा हूँ कि JZ will be diagonal SG plus SG, but HZ. So one has to find out this matrix explicitly. For example, if I were to find out first LZ and finding out the elements of LZ, for example, let me just find out one element for you. Let me find out this element for you. Now this element really is 3 by 2, 3 by 2, LZ 3 by 2, 3 by 2. But the point is that is this an eigenstate of LZ? We have to check this because this is a coupled state. This is written in a coupled basis. However, LZ is a Zeeman angular momentum operator acting on just one degree of freedom, the orbital degree of freedom. So I would like to convert this coupled basis state to its uncoupled variant. This state 3 by 2, comma 3 by 2 is really, now what kind of system I have? I have a 1 crossed half system, which means this is the orbital angular momentum is 1, L is 1. Okay? Because I can have J equals 3 by 2 only for L equals 1. And S is half. So I have a 1 cross half system. Okay? So the only possibility of achieving an Nj value of 3 by 2 is if my, this is 1, this is fixed at 1.
So ये भी 1 होगा.
ये भी 1 होगा और ये अगर half है, ये भी half होगा. When in this kind of labeling represents L, comma ML, cross, and this represents S, comma MS. Okay. So this is the uncoupled or direct product version of this. ठीक है ना? इसको बाजू का यूं ही लिख देते हैं 1, 1 semicolon half, half. ठीक है, मुख्तलिफ बहुत इसको मुख्तलिफ अंदाज में. So I would like to break this up into this form, and if you work it out, this just turns out to be equal to 1. So I would like to represent all the coupled basis states in the uncoupled version. For example, if I have the state 3 by 2 half, then this state is really 1 crossed with half minus half plus 1 0 crossed with half plus half. And now I have to supply coefficients. I have to put in certain coefficients, which are the Clebsch coordinate coefficients. These are picked up from the table. Okay. So this is 1 over 3. I provide you the table in your exam. Okay, this is 2 over 3. So I can express this coupled state as a superposition of uncoupled states. And then I can easily apply the LZ operator on this. Let me do it once. If I apply the LZ operator on this state, LZ acting on this state, 3 by 2, 1 half. Okay. Then I have 1 over 3. Of course, there is always an H bar factor. Now LZ operator acts only on this, and its value of Mn is 1. So I get 1 here, 1 cross 1 half minus half. Okay, plus H bar 2 by 3, 1 0. This just gives me 0. So this is the effect. This is the result of the cat coming out because of the application of the LZ operator. And then I take this inner product with the different states and populate this matrix. Okay. So then similarly I can make SZ. then I can make HZ, and then I can find its eigenvalues. I will get the corrections to the energies. This is something I would like you to do explicitly as part of your homework. Okay. So these problems are also present in the end of the chapter. However, there is a simpler way of doing all of this.
So when we are practicing, do we calculate by applying L minus, or do we simply use the Klebsch-Gordon coefficients?
No, just use the Klebsch-Gordon coefficients. Just use the table.
Thanks.
समझ आ गई करना है कैसे उसको? अच्छा, अब एक और इसी प्रॉब्लम को हल करने का एक और तरीका, ठीक है? वो तरीका is based upon a theorem of quantum mechanics, which is called the Wigner-Eckert theorem. Now the Wigner-Eckert theorem has certain corollaries. It's a complicated theorem, not going to prove it. It has certain corollaries. One of the corollaries is that it gives a formula which is called the projection formula. Okay? So what I've done so far is that I've used the machinery of D-Zeeman perturbation theory, and I've motivated you how you could solve this problem. Now I will use a theorem in quantum mechanics, and I'll use a particular variant called the projection formula. What is the projection formula? The projection formula simply states that if I have an operator, a Z component of an operator, Vz, some operator, some vector operator Vz, angular momentum operators are vector operators, okay, Vz, and then I take its expectation value of Vz in, let's say, J and J, and not the expectation value, but this I can form this inner product. That is J and J in the bra and J and J dash in the cat. This is an inner product. Okay. This is the total angular momentum J, and Mj is one of its projections. Mj dash is another projection. Mj dash may or may not equal to Mj. Okay.
So what can you possibly L?
It can be LZ, it can be SZ, for example. Now this equals, I take the angular momentum operator J, the total angular momentum operator J, and I take its projection along the same axis Z. Okay, and I form the same inner product J and J, J and J dash, okay. So this is one element of Jz, this is one element of Vz, okay, and this has to be multiplied by the dot product of this operator with J, V dot J. Okay, J and J, J and J, not Mj dash, J and J here, and I divide by H bar square J plus 1. So this is the projection here. Projection formula. Let's see how can we apply this. Suppose what I've asked you is, I've asked you to calculate SZ and LZ in the coupled basis, which means that I would like to have elements of SZ which are simply J and J, J and J dash, right? finding the representation of SZ on a particular basis, I would like to find out these elements. And I would like to find out these elements. J, Mj, Lz, J, and J dash. Now let's use the projection formula to easily find out these elements. For example, this, now L is a vector operator and Z is one of its components. So according to the projection formula, this would be equal to J, Mj, total angular momentum of Z component, J and J dash, J, Mj, L dotted with J, J and J, H bar squared J, J plus 1.
Shouldn't that be L as well?
Which one?
J
A? ये तो टोटल आएगा मतलब J को
B जोड़ते हैं तो उसको नहीं लेंगे।
ये B तो यहाँ पे है, ये कोई और वेक्टर ऑपरेटर, ये टोटल आएगा।
So is that Mj prime or Mj?
Where?
L dot J right?
Mj.
ये वाला, ये वाला, ये MJ है, without the prime. ये expectation value L dot J. ठीक है? इसी तरह, if I apply the projection formula, I can find out the elements of SZ in decoupled basis. J, Mj, S dotted with J, J, Mj, J, Mj, Jz, J, Mj dash, H bar square, J, J plus 1. Okay. Now I have to find out what is L dot J and S dot J. Now I know that J, S dot J, for example, is S dotted with L plus S. This is simply L, S dotted with L, which is the hyperfine interaction Hamiltonian, plus S squared. Now S dotted with L we know is half J squared minus S squared minus L squared. Because J is equal to L plus S, J squared is S squared plus L squared plus 2 times S dot L. Okay? So this means that S dotted with J is simply half J squared plus S squared plus S squared. This is S dot J. Likewise, L dotted with J is half J squared plus L dot squared minus S dash. Right? Now let's express L dot J and S dot J, which are really interaction Hamiltonians, in terms of total angular momentum operator and the angular momentum operator magnitude of it for the first degree of freedom and for the second degree of freedom, the orbital and the spinning. Okay? So now these expectation values are quite easy to find. For example, this expectation value is simply going to be equal to half H bar squared J, J plus 1 plus L, L plus 1 minus 3 by 4. This value here is simply going to be equal to half H bar squared J, J plus 1 minus L, L plus 1 plus 3 by 4. Okay. Now this is non-zero only when mj equals mj dash.
Would it be a delta function?
Right. So this means non-zero only when mj equals mj dash. So only the diagonal elements exist for Sz in this basis. This is just by luck. Okay. So only the diagonal elements will exist here because this only exists when mj equals mj dash. This value when mj equals mj dash is simply h bar mj, and this is simply also h bar mj. So now what I have to do, I found out the representation of Lz and Sz in the uncoupled basis. And now what I could do, I could simply find Hz in the coupled basis. This is by luck that the H will be diagonal. Hz J mj J mj dash. This will only be non-zero when mj equals mj dash, and this equals. So it equals J mj Hz Jmj. Okay? So only the diagonal elements exist. I have mu b b over h bar Jmj Lz plus 2Lz Jmj Now I get mu b h bar. Let's look at LZ's. The values of LZ. The values of LZ are given by this. I have h bar square here. H bar square at the top. Right. So the h bar square goes away. This gives me an h bar mj. Okay. So I get an h bar mj. H bar mj. And on top of it, I get LZ. LZ में j plus 1, j plus 1 आगे क्या है?
Plus L plus 1
minus 3 by 4 और I get 2j plus 1 here. Okay, the h bar is this is what I get, plus mu b mj jj plus 1 minus l plus 1 plus 3 by 4 2 times jj plus 1. ये denominator और ये हाफ यहाँ ये वाला ठीक है. तो इसका मतलब ये है कि the elements of Hz in the coupled basis, and the coupled basis is an eigenbasis of the unperturbed Hamiltonian. So what we do, we writing the degenerate subspace, we writing the perturbation Hamiltonian in the degenerate subspace. That's effectively what we're doing, and it turns out to be diagonal. It's diagonal. It means that the diagonal elements will actually give the energy perturbations. Okay, so this turns out to be mu b h bar और एक 2 का फैक्टर है यहाँ पे, ठीक है, एडिशनल 2 का फैक्टर है ये वाला mj j plus 1 plus l plus 1 minus 3 by 4 over 2j plus 1 plus ये 2 इससे कैंसिल हो जाएगा, j plus 1 j plus 1 minus l plus 1 plus 3 by 4. Now I can do a bit of algebra. U b over h bar mj 2j plus 1 I do it j plus 1 3 times j plus 1 minus l plus 1 minus 3 by 4 plus 6 minus 3 by 4 plus 6 by 4 plus 3 by 4. And this is v equal to mu b mj 1 plus j plus 1 minus l plus 1 plus 2 by 4 divided by 2j plus 1. This is just some other, I can lump this together and I call it G sub j. This G sub j in spectroscopy is for the landing G factor. Now look at it, it depends on J and L. So now what's happening is that values in the same stays in the same value of J, but different L, they get different energies. And different energies also are imparted by the different values of Mj. Okay, so the Zeeman corrections to the energies to first order. E first order Mj Zeeman, they are given by Gj mu b d. Mj. Notice if we have just a pure spin half electron, no orbital angular momentum, then look at the factor Gj. Gj will be 1 plus, now J is just S, okay, J is just equal to S, but L is 0. 3 by 4 plus 3 by 4 is 6 by 4 divided by 2 times 3 by 4, 3 by 4 plus 1 is 7 by 4. J is half, oh sorry, 3 by 4. Okay, so this becomes,
So J is half.
J is, so J is half, so this becomes 3 by 4, J into J plus 1 plus 3 by 4 is 6 by 4 divided by 2 times J is half, 3 by 2, 3 half plus 1 is 3 by 2. So 1 plus 6 by 4 into 2 by 3, rho is 2. And we know that for the G factor for a single spin half electron is 2. So this is a general formula. You have an orbit, you have orbital angular momentum coupled with the spin angular momentum, and on top of it you apply a magnetic field. This is how the splitting is going to occur. Gj will be Bmj. Now let's look at an example. Suppose we consider the fine structure unperturbed energy levels and we consider the n equals 2 manifold. Now for n equals 2, you have two possible values of j. You have, now this is the level, the Coulombic level. Now we know that for n equals 2, j has two values, half and 3 by 2. So you can have, and so this is a two-fold degenerate set. This is 2s half, this is 2p half, this is 2p 3 by 2. This is the unperturbed energy level from the perspective of the Zeeman interaction. So now we have the Coulombic energies and we shifted away from the Coulombic energies because of the fine structure interaction. Okay, so we get the 2p 3 by 2 and the WPs and the 2s half and 2p half levels. Because these levels are the same energy because they have the same values of j and the same values of n. Now on top of this, we would like to apply the Zeeman Hamiltonian, that we place this structure inside the magnetic field. And we would like to see how the energy splitting occurs. How is the degenerate selected? So let's first consider the 2s half level. For the 2s half level, j is equal to half, n equals 0. Okay. So for 2s half, for each level we would like to find out the value of Gj, the Lagrangian factor. We've already done that for the 2s half level, it's 2. Because the orbital angular momentum is 0. So there's one possible value of J, that's 1 half, is just a spin half part. Gj is 2. So the energy splittings, the Zeeman energy splittings, E Zeeman, are going to be Gj is 2, mu b, b, and j has two possible values, plus half and minus half, for j equals half. So you get plus minus half, which is plus minus mu bb. So this level is going to be split into two by the application of weak magnetic field. So if I draw the energy level in the presence of a magnetic field, this 2s half level is going to split into two. Okay, so if I draw this datum line here, then one of these levels will be higher in energy, other will be lower. And how higher will it be in energy from the datum line? Plus mu bb. And this will be lower by minus mu bb. So from this datum line, this energy is mu b, this energy is minus mu bb. The value of mj tells you the possibilities of the value of j tells you the possible range of mj's, tells you how many levels you get the splitting. And the value of gj tells you the amount of splitting. It determines the amount of splitting. The amount of splitting here is given by 2 times mu bb. Right? Gj is giving the amount of splitting. Let's look at this level. How does this level split? The 2p half level. For the 2p half level, we would like to find out the value of Gj. Now if you put it into this formula, J equals half, L is now equal to 1. For the p orbital, L equals 1. So Gj equals 1 plus half into half plus 1 is 3 by 2 minus 2 plus 3 by 4 divided by 2 times J is half 3 by 2. Get 1 plus 4, 6 minus 8 plus 3 by 2, 1. 9 में से 8 निकालो, 1/4, 1/4, 2/4. half. J is half. Half plus 3/4 होगा नहीं? Half into half plus 3/4 minus L is 1 minus 2 plus divided by 2 into J is half. Half plus 1 plus 3. 6 minus 8. 6 minus 8 is right? Gj is 2/3. So when Gj is 2/3, the energy splittings E Zeeman for this level are going to be 2/3 mu b, b, and the possibilities of mj. Now mj has two possibilities, half and minus half. So you get 1/2 plus minus. Get plus minus 1/3 mu bb. So if I look at the splitting of these levels, they will also be split into two because mj has two possibilities, and the amount of splitting is given by Gj, which is 1, which depends upon Gj. So this level will also be split into two about its own datum length. This level will be at 1/3 mu bb with respect to the datum length, and this level will be at minus 1/3 mu bb with respect to the datum. थोड़े स्टूडेंट के फील लगता है दीवार को Likewise, we can form the energy splitting of this 2 to 3/2 level. How many levels would it split into? Why? 4. Because mj has 4 possibilities: 3/2, half, minus half, minus 3. So for this level, I can find out the value of Gj. For 2p 3/2, Gj is 1 plus 3/2. 3/2 plus 1 is 5/2. P is still 1, so minus 2 plus 3/4 divided by 2 times 3/2. J is 3/2. J plus 1 is 5. So I get 1 plus 15/4 minus 2 plus 3/4. Get 3 times 15/2. This becomes 1 plus 4, 15, 18, 20 plus 10/4. 1 plus 1/3 is 4/3. So now my possible splittings are, the E Zeeman splittings are Gj, which is 4/3, mu b, b, and now mj can take up 4 possible values. It can be 3/2 or half or minus half or minus 3/2. So you can get levels at 2 mu bb, 2/3 mu bb minus 2/3 mu bb minus 2 mu bb, and the spacing between any two adjacent levels is 2 minus 2/3 mu bb. 4 by 3 dB. So this level is also split up, but now it's split up into 4 levels. So if I draw the datum line here, I get 4 levels. Now these levels are actually really small as compared to these splittings. It's a weak magnetic field. Okay, and I can find, I've already found out the energies of these levels. So this is how the weak Zeeman effect occurs. Now if I have a strong magnetic field, so this is something I would like you to do on your own. If I have a strong magnetic field, then what happens is my Hamiltonian is such that H naught plus HR plus Hz is treated as the unperturbed Hamiltonian. And the spin orbit interaction is much bigger, so it has to be treated as the perturbation. Okay? So now the point is that if the unperturbed Hamiltonian, the eigenstates are no longer the NLSJ states. They become the NL, ML, SMS states, the uncoupled states. So now I would like to write a spin orbit interaction Hamiltonian in terms of the uncoupled states.
We do this through this mechanism.
Through the projection theorem?
We just have to check the.
No, you can't, because what you need to do is you need to find out the spin orbit interactions. Now this is S dot J. Probably yes, you can. Yes, you can. Okay. So treat this as a homework problem and try to do the back of the chapter problems. And then we have the intermediate case in which the field is neither too strong nor too weak. Then you have to write down the full Hamiltonian in either basis and diagonalize it. So please try to do these questions over the weekend, the back of the chapter problems, and then see if we have problems. We will discuss those problems on Monday. Okay? Yeah, we do have a meeting probably next week. Otherwise, week is really tedious. We'll discuss your courses sometime later.